All right, let's talk about writing Lewis structures for molecules that are covalently bonded together. So this, in case you don't remember from last time, this is when we have nonmetals bonded together in a molecule. So if we have a metal and a nonmetal, that would be ionic bonding. These are covalently bonded compounds, so it is going to be only nonmetals in these compounds. And we have a set of rules that we are going to use to help us write or draw the Lewis structures for these kinds of molecules. So the first step here is to write the correct skeletal structure. Now, some of the times this is going to be fairly obvious what the correct skeletal structure is. Sometimes it might be a little bit harder to tell, but we have some good rules of thumb here to follow. Some of them are actually just hard and fast rules, not even rules of thumb. The first one here, hydrogen atoms are always terminal. What that means is you might have something here, some element X, and if you have hydrogen bonded to it, as you'll see in just a second, we're going to represent bonds as a line, like this. If you have hydrogen bonded to it, the molecule doesn't go any farther than that. If you remember, hydrogen only wants a duet. It only wants 2 electrons. And so once it gets these 2 electrons in the bond, because every bond is 2 electrons, it doesn't want any more. It's done. It's never going to form a bond to something else over here, or have, a lone pair or something like that. That is never, ever, ever going to happen. It is just going to be a single bond, and it's done. So the hydrogens are always terminal, meaning that the molecule doesn't continue past that atom. And molecules tend to be symmetrical. So if you have a molecule with one kind of atom, that you have one of that atom, and then you have 3 or 4 of a different kind of atom, you're going to arrange the skeletal structure to make it as symmetrical as possible. And we'll talk about how we do that in just a minute. Once we have the skeletal structure made, we're then going to calculate the total number of electrons for the Lewis structure by summing the valence electrons for each atom in the molecule. The key word here being valence electrons, not all electrons, just the valence electrons. It's a very common mistake that students unfortunately do on exams or on homework or something, is they will add up all the electrons. We are not looking at all the electrons, we are only looking at the valence electrons. Because again, these are the only ones that can interact with other stuff. They're the only ones that can actually form bonds. And when we're considering polyatomic ions, by the way, we have to add or subtract electrons based on the charge on that ion. So if we have something like, sorry, that's right on the edge there, like this, nitrate, we would have 5 valence electrons from the nitrogen. Each of those oxygens would have 6 valence electrons, and then we would add 1 extra because of that negative charge, because that negative charge is telling us we have an extra electron. Because remember, electrons have negative charge, and so if we have a negative charge on this ion, that means we have 1 extra electron. If we had something like this, on the other hand, which I think we'll actually see in just a minute, that positive charge tells us that we're going to subtract an electron. So we would have 5 for the nitrogen, 1 for each of those hydrogens, and then we would have 1 taken away because of that positive charge. It's lost an electron. So our third step here, we're then going to distribute the electrons among the atoms, giving octets to as many atoms as possible, the ones that want them anyway, because remember, hydrogen only wants a duet. We're going to form single bonds first, and actually, as you'll see in a second, when I make my skeletal structure, I go ahead and just put in the single bonds, because they have to have at least 1 bond, and so you might as well just put it in at the beginning, because there's no way for it to have less than that. It has to have at least 1. So the single bonds should already be in there. Then fill the terminal atoms with lone pairs. And then if we have any that are missing an octet at that point, the ones that want an octet, so this is rule number 4 now, if any of them lack an octet after putting in lone pairs on all the atoms that want octets, we can then move those lone pairs around to try and form either double or triple bonds to give things octets that want octets. And so if that doesn't make a whole lot of sense right now, it hopefully will after we do a couple examples here. So we have a few examples that we're going to work through here. And since we have a few of these, I think what we'll do is we'll go ahead and work through the first one together, and then I'll have you pause to work on the second and the third one. I guess technically if you want to go ahead and pause it, you could, and see if you can get the first one right as well, but we're going to go ahead and jump right into that first one, which is CO2. And so we're going to draw the Lewis structure for CO2. If you remember, the first step is to write the skeletal structure, and our guiding principle was that we want to make the molecule as symmetric as possible. So if we do something like this, that's not symmetrical. It's not symmetrical at all. So we don't want to do that. Let me see. How do I... There it is. Erase these things, because that is bad. Nope, nope, nope. We don't want that. So instead, we'll make it more symmetrical, is if we have this. Carbon in the middle, and then 2 oxygens bonded to it. That is as symmetrical as we can make it. And that is the correct skeletal structure for this molecule. So now we're going to add up the valence electrons. And if you remember the shortcut for figuring those out from the previous video, everything in the column with carbon has 4, because that's in column 14. Everything in the column with oxygen has 6. It's column 16. We have 1 carbon and 2 oxygens, so we have 12 from the oxygens plus 4 gives us 16 total. All right. We're now going to distribute those electrons, so we're at rule number 3 now, or step number 3. We already have 4 in the skeletal structure with those single bonds, because remember, each bond is 2 electrons, and actually every time we put in electrons here, we're always putting them in 2 at a time, because all the bonds are 2 at a time, and the lone pairs are also 2 at a time. So we're going to put lone pairs in now on terminal atoms first. So we already have 4 from the single bonds, so starting from there, we have 6, 8, 10, 12, 14, 16. We've run out of electrons. And by the way, it doesn't matter which oxygen you start on. And that'll be the case for everything. It won't matter which one you start with, assuming that they're all the same. So, we put in our 16 electrons. Now we need to check, does everything that wants an octet have an octet? It does not. 2 of them do. Notice the oxygens each have an octet, but the carbon is not happy with us. The carbon only has 4 electrons. So what we're going to do is we are going to move lone pairs around to try and give that carbon an octet. And we can do that by moving this one here, and this one here. So let me erase those. Oops. Okay. So now, if we check, the oxygen has 8, this oxygen has 8, and the carbon has 8. Everything that wants an octet has an octet. Now, if you were looking at this and you thought, well, why couldn't I just do this, 2 lone pairs from this oxygen to make a triple bond here and have a single bond there, and then he would have an octet. And you would not be wrong about that. That would be an acceptable answer if you gave that answer, but it actually is not the best answer for reasons that we're not going to get into at this point. It is a better answer, and it should make sense if you remember we said that we like molecules to be as symmetric as possible. This is more symmetric. But if on an exam you were to give me a triple bond on one side and a single bond on the other, because everything would have an octet at that point, I wouldn't count it as being wrong. But this is a better answer. Alright, so let's do the other two now. So we have CCl4 and ammonium. So C, just make a little box here to block that off. CCl4 and ammonium. So go ahead and pause the video now and try to work out the Lewis structure for these two molecules, or I guess one molecule and one ion. Alright, hopefully you paused the video and tried to work that out yourself. So let's go ahead and work through it together now. So we'll do the CCl4 first. So if we're going to draw our skeletal structure and we want it as symmetric as possible, since we can have 4 things attached to that carbon, because again we're treating all these like they're a 4-sided box, we're going to put all 4 chlorines on that central carbon. This is as symmetric as you can get it. If you swap the carbon with any of those chlorines, it is not as symmetrical. So this is our best option here. If we count up our electrons, we have 4 from the carbon, 7 from each of those chlorines. So we would have 28 plus 4 is 32 electrons. We already have 8 in those single bonds that we put in there with the skeletal structure. Because again, you have to at least have a single bond. And so we might as well put those in at the beginning. So we have 8 in there already. We're just going to pick a chlorine and start putting in lone pairs until we run out of electrons. So starting at 8, we have 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, we ran out of electrons, we only had 32 to give, so the carbon is not going to get any lone pairs. That being said though, does the carbon want any lone pairs? The way we figure that out is we actually try to figure out, does it have an octet? Does it have its 8 electrons? And it does indeed. It has 2, 4, 6, 8. It has 4 bonds. Each of those have 2 electrons. And so that is an octet. Same thing here with the chlorines. Although they don't have 8 in bonds, they have 6 that are lone pairs, or 6 in lone pairs, I should say, and then a single bond. And all 4 of the chlorines have that same situation where they have 1 bond and 3 lone pairs, which gives them each an octet. And so actually, that's it. It's done. No need to move lone pairs around. Everything that wants an octet has one. So what about the ammonium? Well, its skeletal structure is going to look like this. We have nitrogen in the middle, 4 hydrogens bonded to it. How many valence electrons does the nitrogen have? Hopefully you said 5. The hydrogen has 1. It's in column 1. So we have 5 plus 1 times 4, since we have 4 hydrogens, which is 9, but it has a positive charge, and so we actually have to subtract 1, which gives us 8 electrons. So we have 8 electrons in this structure. If we count the number of electrons that are in the molecule already, we have 2, 4, 6, 8, just in the single bonds to the hydrogens. So we actually, just by putting in those single bonds, have used up all our electrons. There are no more to give. So this is the correct Lewis structure. That is the Lewis structure of ammonium. All right, let me see. Do I have any more examples of these? Yeah, so let's go ahead and work on these two real quick. So this is sulfur dioxide and nitrate. Let's go back here to do that. So we have sulfur dioxide and we have nitrate. I have to write these fairly small, but that's okay. So go ahead and pause the video and try to write out the Lewis structure for sulfur dioxide. All right. Hopefully you were able to figure this out as your skeletal structure here. Again, we want it as symmetrical as possible, so we put sulfur in the middle, 2 oxygens on the side. If we add up our electrons, sulfur is in the same column as oxygen, so it has 6. Because again, it's in column 6A or 16. And so the oxygen is in the same column. It also has 6. So we have really 6 times 3 is what it ends up being, which is 18 electrons to go into our structure. We have 4 electrons in the structure already. And so if we just start adding in the electrons, we just pick an oxygen, doesn't actually matter which one. There's 6, 8, 10, 12, 14, 16. Both of the oxygens are now satisfied, and so the last 2 electrons we will put on the sulfur. So if we check to make sure everything has an octet, what we will find is that the sulfur is the only thing that does not have an octet. And so to make the sulfur happy, we can either move an electron, move a lone pair, I should say, from this oxygen over here to make a double bond, which would give the sulfur its octet, while still keeping this oxygen having an octet. So that would look like this, because those would go away. Or we could also have done the same thing, but with the other oxygen. And truth be told, it doesn't actually matter which one we do that with. This is what we would call a resonance structure, where there are 2 different structures that are both just as reasonable as the other. So it has more than one acceptable Lewis structure. These are called, again, resonance structures. So unless I specifically ask you to give me more than one of these, if on an exam I ask you to either identify or to somehow draw the correct structure for sulfur dioxide, I would not expect you to give me both of them unless I specifically say in the problem, identify both of the acceptable resonance structures. But if I just ask you for a single one, then this one's fine. It's no better or worse than having the other oxygen be the double bond. Similarly here with the nitrate, if we put nitrogen in the middle, I'm going to run out of space here, but oh well. Bond the 3 oxygens to it. If we add up our electrons here, nitrogen is in column 15, so it gets 5 valence electrons. Oxygen is in 16, so it gets 6, and there are 3 of them. And then we're going to have one more because of the negative charge there. So this is 18 plus 5 is 23, plus 1 more is 24 electrons. So if I count up the electrons I have in the single bonds, that is 6. Starting from there, I have 8, 10, 12, 14, 16, 18, 20, 22, 24. I've run out of electrons, and the nitrogen is not happy. The nitrogen does not have its octet. And very similar to what we had with the sulfur dioxide, we have options as to where we can make the nitrogen happy. Any one of these oxygens could form a double bond to make the nitrogen have its octet. And very similar to the sulfur dioxide, it doesn't actually matter which one we use. So just because I think it looks better, I'm going to do it with the middle one there. In reality, there isn't actually a middle one. The actual 3D structure of the molecule is not represented accurately here with the Lewis structure, as we'll talk about in the VSEPR video. So I'm just going to do the middle one there just because I think it looks better. All right. I think that will be it for this video. In the next one, we are going to talk about VSEPR. And I am absolutely sure that we will talk more about Lewis structures and do more practice problems with Lewis structures in the discussion and help time during the week. I'll see you in the next video.